Hello and welcome to the Autumn 2 Week 3 exam marking video. This was the exam on crude oil and fractional distillation. Okay, the first question. Crude oil is a fossil fuel. To make crude oil more useful, it is separated into fractions. Use the correct words in the box to complete each sentence. First sentence. Crude oil is a what of different substances? If it can be separated, it must be a mixture. Crude oil is a mixture of different substances. That should be a fact that you just know. The substances in crude oil have different what points. Perhaps you don't know it, in which case it shouldn't be hard to go through. Different molecule points, doesn't make sense. Different mixture points, no. Filtration points, compound points, decomposition points, distillation points, boiling points. That sounds about right. And you should know that the substances in crude oil, namely fractions, have different boiling points. Petrol is one of the fractions. Fractions, we've seen it up here, and you should know that is one of the substances produced from crude oil. Car engines use a mixture of petrol and air. Green chemistry revision for you. What are the substances in air? Got 4 arrows. There should be 4 substances that you should be able to name that make up air. I'll give you the first. Oxygen, of course, which we need to respire. Carbon dioxide, the greenhouse gas. Most of air is formed of nitrogen, and finally, of course, water vapour. Another greenhouse gas. Methane you might have got as well. The car engines have got petrol, and then they've got that little lot going on inside the car engine as well. The diagram shows some of the gases produced. There's the diagram. So we've got petrol, and they have helpfully written oxygen in air for you. Now I've put a little addition sign, because that's what's going in to the car, right? And then the reaction's happening inside the car, and then here's what's coming out of the car: carbon dioxide, nitrogen, and water vapour. The addition sign is just like an addition sign on a chemical reaction. They're the reactants, petrol plus oxygen, and these are what's being produced. What type of reaction is going on inside that car? Petrol and oxygen going in, carbon dioxide, water vapour stuff coming out. What kind of reaction is it? We need to tick one of these boxes. Combustion reaction. Combustion, you should know, essentially means burning, and in order to burn, it always requires oxygen. So that's sounding likely. Decomposition is when something breaks down. Neutralisation, acid plus a base. What is going on, I can tell you, is burning. Okay, the petrol is being combusted in the oxygen inside the car and producing those gases that come out the other side. Moving on, petrol contains octane, C8H18. Now I just want to check that you can identify what octane must be. First of all, it's ANE, and ANE, that should be a hint, and also it's made of carbon and hydrogen. It is therefore a hydrocarbon made of hydrogen and carbon, C and the H, and it's an alkane as well. We know it's an alkane, it ends in ANE, it's not an alkene, which would end in ENE. The other way we know it's an alkane is by looking at the equation. It fits the general equation for an alkane, which is CnH2n plus 2. In this case, n is 8. 2n plus 2, 8 times 2 makes 16, plus 2 is 18, correct, so it's an alkane. Complete the word equation for the reaction of octane with oxygen. Okay, octane, I've just jotted that down there, it might help us when we're figuring this out. With oxygen, so the next reactant should be easy. We are reacting octane with oxygen, so that's 1 mark for saying oxygen. By the way, I've underlined word equation. These should be written as words, not as formulae or symbols. Then requires a bit of thinking. What happens when you combine octane, so a hydrocarbon, with oxygen? Well, we've got carbon, we've got hydrogen, and we've got oxygen. What will come out the other end? It's definitely not going to be anything like nitrogen, for example, because none of the reactants have nitrogen. We've got carbon dioxide, or you could have written carbon monoxide, would be fine as well. So some of the oxygen reacts with the carbon, And then we've got some hydrogen as well, which is left to react with oxygen. When you combine hydrogen and oxygen, you get our good friend H2O, makes water. Now it would be fine if you'd written water vapour, it would be fine if you'd written hydrogen oxide, but any combination of hydrogen and oxygen here, and a combination of carbon and oxygen here, carbon dioxide or carbon monoxide, is fine. Right then, cars use sulphur-free petrol as a fuel, sulphur another element. Petrol we know is a hydrocarbon. Describe why sulphur should be removed from petrol. Now, reading this question, my thought is, okay, if I need to describe why sulphur should be removed, I'm going to think what would happen if it wasn't removed? What would happen if it did have sulphur in? You need to use the knowledge from further up in the question that petrol combusts inside an engine, so petrol burns in the presence of oxygen, and then you need to know the answer to this. What happens if you have sulphur and you combust sulphur in the presence of oxygen? Hopefully you know the answer to that. If you burn sulphur in oxygen, or just burning sulphur, so it requires oxygen, produces, a moment to think about it, we've got sulphur and oxygen, sulphur dioxide, and you could have written the formula for that instead, SO2. It would be fine if you just said that the sulphur reacts with the oxygen. Ideally you know that it produces sulphur dioxide. Why is it important that you know it produces sulphur dioxide? Because that in turn produces something not very nice, acid rain. Okay, so if they didn't remove sulphur from petrol, it would produce sulphur dioxide and therefore lead to acid rain. That's the answer that you need to describe why sulphur should be removed. Moving down, some fractions from crude oil contain large hydrocarbon molecules. These molecules can be cracked to produce smaller, more useful molecules. Now this information is really useful and it will come in useful later in the exam. Cracking is breaking down a large hydrocarbon molecule into a smaller hydrocarbon molecule. And here's an example equation. We've got decane, which is our large hydrocarbon molecule. How do we know it's large? It's got 10 carbons, and then that's being broken down into smaller hydrocarbon molecules, and this process is called cracking. How do we know they're smaller? Well, propane's only got 3 carbons compared to the larger 10, ethane's only got 2 carbons compared to the larger 10, and pentene only has 5 carbons compared to the larger 10. Okay, so the large one has been broken down into smaller ones. Then the question is, why is propane useful? Now this just requires a bit of a knowledge of your hydrocarbons. A few words that you might not know. A polymer, propane is a polymer. Polymers are usually a type of plastic, and they are formed from alkenes. So if you didn't know that, if you didn't see that blank and think I know exactly what Miss Clear's talking about, you need to learn that. Alkenes are used to produce polymers. So you can rule that one out. Propane is definitely not an alkene, because propane is an alkane. It's got an A in it rather than an E in it. So it's not propane as a polymer. Propane is an alloy. I mean, to rule that one out, you need to know what an alloy is. So I've written the definition there. An alloy is a mixture of 2 elements. One of them must be a metal. The famous one is steel. Steel is an alloy of iron. So it's a mixture of iron, which is a metal, with some other elements. Propane is an alloy. Now let's have a think. Propane is C3H8. We've got carbon and hydrogen, both non-metals. So propane definitely isn't an alloy. An alloy requires 1 metal. Therefore propane is a fuel, is your correct answer. Now hopefully lots of you knew that anyway. One of the main uses of hydrocarbons is as a fuel. Okie dokie, draw bonds to complete the displayed structure of ethene. And now we're going into the alkenes. Up here I was mentioning alkenes. Now we have an alkene. Ethene is an alkene, we know because of the E's. Alkenes are unsaturated, which means that they have a double bond. You'll see what that looks like in just a moment. Okay, that's in comparison to an alkane. An alkane is different from an alkene. It is saturated and it has single bonds. In this case, they're asking us about ethene, which is an alkene, so we need to draw double bonds. The double bonds in alkenes go between the carbon molecules. We've got a double bond there. Unsaturated means that those bonds can then react. Okay, those bonds can react elsewhere, which means alkenes are more reactive than alkanes. What is the colour change when bromine water reacts with ethene? Next question, we need to tick one box. Reading this, you should have thought bromine water is the test for whether something is an alkene or not. If it is an alkene, then there will be a colour change, as this question suggests. So ethene is an alkene, there is going to be a colour change. If it isn't an alkene, if it is an alkane, like ethane, then there is no reaction and there is no colour change. In this case, ethene is an alkene, so there will be a colour change, and you need to know what the colour change is. All of them start as orange, and the knowledge you need to have is that it becomes colourless. Right, moving on. Question about crude oil, surprisingly. This table shows information about crude oil fractions. Let's just have a little look at the table before we move on, so that I know that you understand. We've got a whole load of fractions from crude oil, so crude oil can be separated into these different substances. This tells me how long the fractions are. Okay, so I'll just leave you for a moment to think, do they start off as long chain hydrocarbons, or do they start off as short chain hydrocarbons and then get longer? Or do they start off long and get shorter? The answer is they start as short chain hydrocarbons, so gas, it has up to between 1 and 4 carbons in its chain, and then it moves all the way down to very long chain hydrocarbons down here, which have between 20 and 30 or more carbons in a chain. And then it tells me how much there actually is in crude oil. That's what this column is telling me. So if you actually just separated out crude oil, we've got not very much gas, more petrol, similar amount of naphtha, more kerosene, more diesel, and then almost half of the crude oil, it forms residue. So that's telling me how much there actually is in my crude oil. This column, demand, is how much is required, how much that actual fraction is useful. Gas, not particularly required. Petrol is required quite a lot. You should be familiar with petrol because it goes in our cars. So the reason why the demand for petrol is so much higher is because we use it in our cars. Naphtha, not a huge demand. Kerosene, not a huge demand. Diesel, again, a large demand for diesel, and the reason is the same, it goes in our cars. And then the residue has a high demand as well, but you'll notice it's smaller than the how much there actually is. Now, the reason I've gone through that and taken the time to go through that is because the question asks us to explain the advantages of cracking hydrocarbons. You'll remember this definition from earlier. Cracking is when you break down large hydrocarbons into smaller hydrocarbons. They're asking why is it useful to break down large hydrocarbons into smaller hydrocarbons, and it asks us to give an example. The first mark actually here is just to explain what cracking is. So you get 1 mark for saying breaking down large molecules into small molecules, or smaller molecules. Then you need to explain why that might be useful. And this requires a bit more thinking. Let's have a look again. Draw your attention to petrol, I think is the best example here. There actually isn't much petrol when you separate crude oil. You only get about 9% of it actually becomes petrol. There's a large demand for petrol. So it becomes useful to break down these larger hydrocarbons into smaller hydrocarbons. Okay, that's one example that you could have given. Another example is this one here, breaking down a larger hydrocarbon into diesel is again useful. Why? Because those are the ones with the biggest demand. Okay, The reason I'm not circling the residue is because the actual amount there is of residue meets the demand. So how much there actually is enough for how much is required. Whereas for diesel, there's not enough to meet what's required. For petrol, there is not enough to meet what is actually required. Okay, so the advantage of breaking down the larger ones is to meet what is required or what the demand is. How can we put that in words? Breaking down large molecules into smaller molecules is useful to meet demand, or to put that in other words, to ensure there is enough what people require. Anything along those lines. Okay, referring, you need to notice that this is how much people require. This is the demand, and we need to break down those large ones so that we have enough petrol and diesel to meet what is required. If we didn't break that down, we wouldn't have enough petrol or diesel to meet the requirement. And then you need to give an example. So I've been talking about petrol or diesel as the examples, and you're saying using numbers, so let's pick one. If you're talking about petrol, you would say there's only 9% of crude oil is made up of petrol, and it has a 23% demand. Or you write the equivalent for diesel. Okay, for diesel you would be saying that the residue needs to be broken down into diesel so that it meets the demand of 22%, whereas only 16% of crude oil is actually made up of diesel. Moving down. Crude oil is a mixture of many different chemical compounds. We know about that. This is a very similar question to the others we've been answering. Table giving us information. Let's just have a little read of the table, make sure we understand. We've got decane, ethene, interesting. It's got an E in it. Icosane, methane. Let's just have a look at the second column, the chemical formulas. What information is this giving us? It's telling me how many carbons and hydrogens are in each hydrocarbon. Now, which one of these is the longest, I've asked. Let's have a look. Decane has 10 carbon atoms in its chain. Ethene has 2, so that's smaller. Icosane has 20 long, and methane only has 1. So icosane is the longest, and methane is the shortest, with only 1. Let's have a look at these two columns. Melting points, okay, self-explanatory. Boiling points, okay, self-explanatory. Next question, which compound is in the table is a liquid at room temperature? And they've told you that's 20 degrees. Very useful. This is how we figure out what states of matter different substances will be at different temperatures. We've been given the melting point and boiling point. Oops, they act on a scale like this. Draw the melting point, draw the boiling point, and you're left with your 3 states of matter. One there, and one there. Below the melting point, if it's colder than the melting point, then the substance will be a solid. If the temperature is somewhere between the melting point and the boiling point, the substance will be a liquid. And if the temperature is above the boiling point, the substance will be a gas. All I've done is copied out these numbers down here, so we can identify for each substance what state it will be in at 20 degrees Celsius. So for decane, 20 degrees Celsius is higher than minus 30, so it's over here, and it's less than 174. So decane will be a liquid. Ethene, 20 degrees Celsius, it's higher than the melting point and it's higher than the boiling point, so ethene will be a gas. Icosane at 20 degrees Celsius is lower than the melting point, so icosane would be a solid at room temperature, and methane at 20 degrees Celsius, well, it's definitely higher than the melting point, it's definitely higher than the boiling point, it is a gas. We know about that, it's one of the greenhouse gases, of course. Question was, which one is a liquid? There is only one, and it's decane. Move down. Which compound in the table has the highest viscosity? Now, a little reminder, viscosity means how thick and gloopy the substance is. You need to know this relationship between length of hydrocarbon chains and viscosity. So I've got two little sentences to fill in. As the length of the hydrocarbon chains increases, so as they get longer, what happens to viscosity? Does it get thicker as the chains get longer, or does it get thinner? Viscosity increases as well. As hydrocarbon chains get longer, the substance is getting thicker and gloopier. Another way of looking at that, long chain hydrocarbons are more or less viscous than short chain hydrocarbons. So a long chain hydrocarbon, will it be more viscous or thinner, less viscous than a short chain? It will be more viscous than short chain hydrocarbons. Okay, so you need to have understanding of that. Now let's have a look. We want the one with the highest viscosity. We therefore want the longest chain, because long chain hydrocarbons are more viscous. Which one has the longest chain? We've already done the hard work here. Icosane. So the longest chain hydrocarbon will be the most viscous. Moving on. Which compound in the table can be used to produce a polymer? Now, I've told you this before. Polymers are produced from alkenes, the unsaturated hydrocarbons. And I even pointed out when we read it, that funny little fact that ethene had an E in it. The others are all alkanes, they have A's. Ethene is an alkene. Okay, so there is only one alkene in this table, there is only one hydrocarbon here that can be used to produce a polymer, and it's ethene. Right, moving down. Diagram 1 shows a kite flying in the air, lovely diagram. I'm sure you'll spend your weekends flying kites. The kite string is made from polypropene. So we've got propene is the alkene with its E, and polypropene means it's the polymer that is made from propene. So propene is an alkene. Poly, brackets propene, is the polymer, and that's easy to remember, they've both got poly, made from the alkene, which was called propene. Okay, so alkenes, like propene, can turn into polymers like polypropene. Diagram 2 tells us the structure of propene, which is the alkene. Okay, so that's the alkene on its own. Notice the double bond, which means it is unsaturated. Okay, alkenes, double bond, unsaturated. They've asked which structure represents polypropene. Okay, so when propene becomes a polymer, what happens? These bonds, I like to imagine them flipping out to the side and like holding hands with the next molecule. That's how I imagine it. And then we draw the double brackets around, and those bonds are sticking out at the side. Okay, so we're looking for this pattern to be the same. H, H at the top, H, CH3 on the bottom right. But instead I want brackets around, and I want two bonds sticking out to the side. You then write the letter N at the bottom, which means that there are lots of those, any number of those holding hands side by side. Tick one box, which one represents polypropene. Okay, remember we're looking for HH at the top, boom, 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 so that rules out C and D. And then we're looking for H, CH3 at the bottom. That looks good, that one doesn't. So our answer here is A. Polypropene looks like that. Next question. Crude oil is a mixture of many different carbon compounds. Haha! Talking about crude oil. Surprise, surprise. Crude oil can be separated into useful fractions by fractional distillation. Blah, blah, blah. Column used to separate crude oil. Now, we would be bugging this. We've come across these things before. We understand these ideas. Here's the fractionating column. Crude oil going into a furnace, going into the fractionating column. Could be called a separating column. And then we've got these different levels of fractions. Now, you need to understand which ones have long chains, which ones have short chains. If you don't know this already, you've got to learn it. The shorter chain hydrocarbons are formed at the top, and then they get longer and longer and longer as we go down. And at the very bottom we have the longest chain hydrocarbons. Okay, so refinery gas the shortest chain, residue the longest chain. One little table that's useful to know, I find, is how the length of the chain relates to viscosity, how thick it is, melting point and boiling point, and flammability. Long chain hydrocarbons, if we've already been through this, are more viscous. So I'm just going to draw a little up arrow. You could write more viscous than short chain. Short chain hydrocarbons are less viscous. Long chain hydrocarbons and their melting points, a very interesting one. Long chain hydrocarbons have a higher melting point, boiling point, than short chain hydrocarbons. Okay, short chain hydrocarbons have a lower melting point or boiling point. The reason is more energy is required to break the bonds in the longer chain. Okay, there are more bonds. Flammability is the opposite. So we've gone more viscous, higher melting point, less flammable. For short chain, they are less viscous, they have a lower melting point, but they are more flammable. Righty-ho. So, with that knowledge, we're ready to answer the next few questions. Which fraction is the most viscous? Let's check viscosity. Most viscous, long chain. Okay, which is the longest chain that we've got? Engine oil. Residue means what's left over. Okay, we'll call it leftovers. Which is why they've not given residue an option. So engine oil is the next longest. Which fraction is the most flammable? Check back at my table. Flammable. The most flammable is going to be the shortest chain. Okay, long chains are less flammable. Short chains are more flammable. The shortest chain that we've got on diagram is refinery gas. So that's the most flammable. Why does kerosene separate out of the mixture before diesel oil? Okay. I mean, actually, interestingly, some of you might have spotted this. I've got it the wrong way around here, but that's fine. We can use our knowledge here to answer that question. Why does kerosene separate out of the mixture before diesel oil? Well, it condenses first. Okay, it's going to condense first because it has a, let me get this right before I tell you the wrong thing, it's going to condense first because it has the lower boiling point. Now, that's the answer that's on my mark scheme. If you said it will condense first, you're right, but you need to talk about it having a lower boiling point. Okay? Right then, over the page. Diesel is separated from crude oil by fractional distillation. Describe the steps involved. So this is just a describe question proving that you know how fractional distillation works. Starts off with gaseous crude oil put into the fractionating column. Okay, in order to make crude oil into a gas, we need to heat it up to a gaseous state. There's no point putting liquid crude oil in a fractionating column, it will not do its job. Once you've got crude oil in a gaseous state, so here we've got it being heated up, going in a gaseous state, it starts to rise up, and as it rises up it cools, and as it cools, what starts to happen? Things start to condense. Okay, vapours or fractions or different substances condense. Good. Then, crucially important, they don't all condense at the same time. Some condense before others. They condense at different temperatures. Some condense when it's still quite hot, some condense when it's getting colder. So at different temperatures. If you've written that idea of some condense when it's hotter, some condense when it's colder, correct, you can have that mark. If you've written because they have different boiling points, correct, you can have the mark. The reason they condense at different temperatures is because they condense when they hit their boiling point. Okay, so only 3 out of those 4 points. Those 2 you can have either or. Right, diesel is a mixture. Mixtures, not chemically bonded. Just a bit of revision there, won't do any harm. Okay, so they're two or more different elements, not chemically bonded together. Diesel is a mixture of lots of different alkanes. What are alkanes? When you see a question like that, you think, what am I comparing it to? Compare them to alkenes. Make sure that you don't just say they're hydrocarbons. What's special about alkanes rather than alkenes? Yes, you get 1 mark for saying they're hydrocarbons. But more importantly, we need to separate them from alkenes. Now, I've gone on and on in this video about what alkenes are. Alkenes are unsaturated and have what kind of bond? A double bond. So alkanes then should be nice and easy. They are saturated. Now you might have said only have single bonds. Don't have the double bond. Okay, it is not enough just to say they're hydrocarbons. If you've put the general formula, that gets you both marks. That's the general formula for a hydrocarbon, and it gets you 2 marks. If you've said they don't have double bonds, that also gets you the second mark, but you do need to still say that they're made out of hydrogen and carbon. Right then, whew, nearly there. One more table, I think, to get our heads around. Yeah, one more table. Crude oil and natural gases are natural resources in many countries. That means they are made naturally. Okay, they form naturally. You should be thinking, you see natural resources, you should be thinking, oh, how does crude oil get formed? We have taught you. Did you think this when you were reading the question? You might as well answer that, I suppose. How does crude oil get formed? It's formed from the remains. Are you thinking what I'm thinking now? Of living organisms, e.g. plankton, buried under layers of mud and rock, etc. Okay, formed from the remains of living organisms. That's where we're getting natural resources from. The reason that exams give you sentences like this is to try and help you. So you want to spot things like that and think, okay, it's formed from the remains of living organisms. Because when you have that knowledge, it makes the answering the next question much easier. Suggest why natural gas from different countries have different percentages of hydrocarbons. We can see that, okay? Country X has less methane than country Y, and then country Z has the most methane. So we can see they've got different percentages of hydrocarbons. It's asking why, and it says suggest. So we've got to use our kind of imaginations here. We've got to think about this one. They are formed from the remains of living organisms. Are all living organisms in all countries the same? No, they're not. Okay? Different types of biomass. If you'd named plankton, good. Different types of biomass or plankton formed the different crude oils. Or sorry, the different natural gases. Okay. Moving down. Complete the sentence, choose the answer from the box. An atom, electron, an ion and a molecule, testing your knowledge of these. The formula CH4, you should know what that is. 1 carbon, therefore it's the shortest alkane, it's methane. CH4 represents a what of methane? Okay, well, is it an atom? No, an atom is just one single thing, so that's a carbon atom. This thing has 1 carbon atom and 4 hydrogen atoms, so it's definitely not an atom. Is it an electron? No, it's definitely not an electron. We've got a whole carbon atom, we've got 4 whole hydrogen atoms, we've got quite a few electrons there, so not that. An ion? No, we know that an ion needs to have a charge. That's not got any charge on it, so it must be therefore a molecule of methane. Complete the sentence. The hydrocarbons in the table belong to the homologous series of blank. Now, one thing I just wanted to put, because I saw a few people made this mistake, it doesn't say choose answers from the box. So if you wrote atom, electron, ion or molecule there, then you're a bit of a twit. Okay? It does not have to be a word from the box. It doesn't have this sentence here saying choose the answer from the box, so don't write a word from the box. Homologous series, interesting. I have taught you there are 2 types of things in a homologous series. If I give you one, I reckon you can work out the other. It's either an alkane or you've got an alkene. We have to decide whether these things, the hydrocarbons in the table, are alkanes or alkenes. How do we do that? Have a look at this little letter here. They're all alkanes. They all have an A in them. They would be alkenes if that was methane, ethene, propene, and so forth. Final question. Nearly there. Crude oil is fractionally distilled. Fractions with larger molecules are cracked. So we know what fractional distillation is. That's the separation into fractional distillation, separating into fractions. Fractions with larger molecules are cracked. We know what cracking is. That's breaking down into smaller hydrocarbons. Good, so we know what they are. Now we have to use our brains a bit and describe two differences between them. Okay, a couple of things you could say. I think, well, first of all, just say the obvious. Crude oil is separating, fractional distillation is separation, whereas cracking is breaking down. That's just showing that you know something about these things. Yeah? If you know it, show that you know it. Molecules. Now, I think the easiest second difference for me is that to separate is simply a physical process, right? If I've got two pens mixed together and I separate them, it's a physical process. I can put them back together again if I want. Just mix them back together and then I can separate them up again. Okay, so separation, fractional distillation, is a physical process. It's reversible. There are no making or breaking of bonds going on. It's just those things were mixed together and then they've been separated. Cracking is a chemical process. There is making and breaking of bonds. We know there is because those larger bonds need to get broken in order to make smaller molecules. So that, I think, is the next most obvious difference between the two. But you could also say cracking uses a catalyst. Whereas fractional distillation doesn't. That's also on the mark scheme, so if you've said that, you can have it. I think these two are the obvious ones to write down. And there we are. End of the exam. Well done for listening. Hope you've made good notes. Please do go over it again. Anything that you haven't understood, anything you need to revise, the video is here for